A few logistic announcements. The website for this course is here. On this website, you will follow a link, academics, courses taught, and you will see Magnetism 2016. I will not upload material onto LMS, and communication with the class will take place through a Google Groups mailing list. I will be assisted by my PhD student Ali Akbar. So please share your Gmail addresses if possible with Ali Akbar so that we can do instant communication through Gmail. So magnetism, as you all know, is one of the basic necessities of life. Just like you breathe oxygen, electricity is unimaginable without magnetism. If we did not have the generators that generated electricity, life would be unthinkable. Without magnetism, you wouldn't have fancy refrigerator magnets, but beyond that, you would not even be able to have memory elements, because all your hard disks, all the memory storage devices are based upon magnetic phenomena. Magnetism economically is a multi-trillion-dollar industry. But at the heart of these magnetic phenomena lie basic principles of quantum mechanics, condensed matter physics, and statistical mechanics. So in this course, what we're trying to do is we're trying to understand the underlying mechanism of magnetism so that we can describe and understand two objects. One are magnetic materials, and the other is our magnetic devices. And the underlying principles all stem from quantum mechanics. So what we will try to do in these 4 or 5 months of our interaction with magnetism is we'll try to look at the fundamental principles, and we'd like to bridge the gap between principles and research and materials and devices. So it's going to be a rigorous course. We're going to be fast-paced. The goal is to get you started with research in magnetism. And magnetism is a huge area. It forms the basis of what we call spintronics as well. The spin degree of freedom of an electron is currently one of the most promising aspects of futuristic computing technology. So this is going to be an exciting course, a rigorous course, stemmed within mathematical principles. It will show you nice applications of quantum mechanics, nice applications of statistical mechanics and thermodynamics. And of course, basic electromagnetism is also at the heart of magnetism that we study. I assume that you are all familiar with quantum mechanics, you're all familiar with Maxwell's equations, and you're all familiar with statistical mechanics, because these are going to be the pillars upon which this subject is going to stand. Alright, so any questions about the logistics of the course? So what we're going to start off with is the concept of orbital angular momentum and spin, because this is what forms the basis of magnetism. Remember, from an electrodynamics perspective, whenever you stick a refrigerator magnet, it's special relativity at work. So unknowingly, relativity is a very mundane and terrestrial phenomenon. Whenever you work with magnets, magnetism is describable in the language of special relativity. So I forgot to mention relativity. Relativity is also at work when you're dealing with magnets. And we'll discuss more relativistic aspects when we talk about spin-orbit interactions, etc. So orbital angular momentum, the basic concept which is enough to motivate the subject is, suppose you have a proton and an electron. In the classical model, the Bohr model, the electron, which carries a charge -e, is circulating around the nucleus. Now we all know that the current that is associated with this electron is given by -e times the time period. And if the radius of this orbit is r, which could be taken to be the Bohr radius if this atom is in the ground state, then this current is -e over 2 pi r v, where v is the speed of this electron. Now what I would like to do is, I would like to find the magnetic moment of this orbiting electron. So now what we effectively have is a charge that is oscillating, going around a nucleus, and this revolving charge forms a current. Associated with this loop of current, there has to be a magnetic moment. And magnetic moment is simply a circulating charge. So if the electron is going around this direction, the angular momentum of this electron, which is denoted by L, is in the direction shown. And if we talk about the magnetic moment would be in the opposite direction. This magnetic moment, we all know its magnitude is given by I times the area of the loop. Now the area of the loop is pi r squared. So what we have is -e over 2 pi r v into pi r squared. So this turns out to be -e over 2 r into v. Now if I multiply by m and divide by m, this is the relationship that I get. Now this m is the mass of the electron. So now what we observe is that the magnetic moment is related to the mass, the product of the speed and the radius. And if you know from basic mechanics, could you identify what this object is called? What is MVR? It is the orbital angular momentum of this electron. So this electron has an angular momentum associated with its shear mechanical motion, the orbital motion. And that is proportional to the magnetic moment of this electron. So the magnetic moment turns out to be equal to -e over 2 times the mass of the electron into the angular momentum. And since the angular momentum is a vector, the magnetic moment is also a vector. So this is quite a nice relationship, and this is the starting point for a discussion on magnetism. A revolving charge that carries an orbital angular momentum has with it associated a magnetism. That magnetism is quantified through the magnetic moment. The units of this magnetic moment, of course, are amperes meter square. Remember that we will stick to SI units in this course. So associated with the orbital motion, the orbital angular momentum, there is a magnetic moment. Now we can generalize this statement. Any moving charge, Q, we can have the mass of a charge, or we can talk about the mass of an electron or the mass of a proton. So this object multiplied by the orbital angular momentum of this object and some proportionality factor, G, let's call it G, will give rise to a magnetic moment. So whenever you have a charged particle and you form this ratio, the charge of that particle divided by 2 times the mass of, for standardization you can talk about the mass of a proton. This quantity has certain dimensions. You multiply this with the orbital angular momentum or any angular momentum and have a constant of proportionality, because this is a measurable. So you perform experiments to measure the magnetic moment, so the constant of proportionality comes either from theoretical motivations or from, and is verified by experiments. So you have a constant of proportionality, which is called the lambda G factor. Then this gives rise to a magnetic moment. The upshot is that associated with an orbital angular momentum, there is a magnetic moment. Even neutrons that are uncharged, the charge on a neutron is zero. It has an orbital or a spin magnetic moment associated with it. There is magnetism, even though it's uncharged. So if you would talk about neutrons, you would put the charge of a proton here and the mass of a neutron here, and you will adjust your value of G accordingly so that you get the correct magnetic moment. The basic principle is that whenever you have an angular momentum, associated with it is a magnetic moment. And what is a magnetic moment? This circulating electron or circulating charge. Let's talk about a general charge. This charge that is moving with a speed v, associated with it is an angular momentum L, and then we have a magnetic moment mu. This orbiting charge produces a magnetic moment, and this magnetic moment can be visualized as a tiny magnet which has a north pole and a south pole, and you can visualize magnetic moments by arrows. So this arrow could represent the magnetic moment, and you can have these arrows pointing in any direction in space depending upon the angular momentum. For an electron, you observe that the orbital momentum and the magnetic moment, they are opposite in direction because the charge on the electron is negative. So now you have, suppose you have a box, and in that box there are electrons. Now each electron may have an orbital angular momentum, and associated with it there could be a magnetic moment. So you have this box of electrons and you have magnetic moments pointing in arbitrary directions. So you can have a soup of magnetic moments. And if it's a gas, these magnetic moments could be pointing in random directions if you don't have any external magnetic field imposed. So you have a soup of magnetic moments. Each one of them could be an electron. Now associated with the orbital angular motion of an electron, there is a magnetic moment. However, we know that mu equals, for an electron, let's talk about general charges. You have a lambda G factor, Q over 2 times the mass of the particle and an orbital angular momentum. For an electron, this Q is minus E. The mass is the mass of an electron, and G is 1, as we just noticed, right? So this is the relationship for an electron. We know that, however, we know that this angular momentum is a quantum mechanical object. So this is really an operator in quantum mechanical terms, which imparts an operator characteristic to the magnetic moment. Right? So orbital, this is an observable. So you can measure orbital angular momentum. But the electron, if it's in the ground state of a hydrogen atom, for example, if you have an electron in the s orbital, in the s orbital, we know that the azimuthal quantum number is 0. And the orbital angular momentum L, which is given by L into L plus 1, h bar must be 0. So an electron cannot be, in its ground state, cannot be magnetic because its orbital angular momentum is 0. Yet, if you perform the famous Stern-Gerlach experiment, which was performed in the late 1920s by Stern and Gerlach, and they accidentally discovered that the beam of silver atoms in which the valence electron was in the ground state, the valence electron had an angular momentum L of 0, still it responded to magnetic fields. Therefore, it must there must be some magnetic moment associated with an electron even when L is 0. And this is how the concept of spin was discovered. So now we know that the electron not only has an angular momentum associated with its orbital motion, it also has an angular momentum associated with its spin, which is a purely quantum mechanical phenomenon. So now we have the same relationship. We could have any angular momentum here. We just would use the proper value of this lambda G factor to find out the correct magnetic moment. The proportionality holds throughout all cases. Either this could be a spin, this could be an orbital motion. You have to adjust for the proper constant, but the proportionality persists. So if you have an electron or a charge with an orbital angular momentum L, we know that the magnetism associated with this object is going to be equal to G. Now let's put an L with this to denote that this is the lambda G factor associated with the electron, orbital angular momentum, and then you have Q over 2m Gs. So now this is a vector, a magnetic moment associated with the orbital and a magnetic moment associated with the spin. Both of these are vectors, and you add them up to find out the total magnetic moment of an electron. Turns out we know that this factor is 1 for an electron. This factor is almost 2 for an electron. The lambda G factor for an electron associated with the spin is 2.002. It's almost 2. This deviation of 0.002 with respect to 2 is about 0.1% deviation from 2, comes out from quantum electrodynamics, and it gives rise to the Lamb shift. But this factor is almost the same as 2. So for an electron, what you have is a magnetic moment which is given by minus E over 2m L plus 2s. This is the magnetic moment of an electron. If the electron has 0 orbital angular momentum, say if it's in the hydrogen atom and it's in the ground state, then the magnetic moment is purely due to the intrinsic spin of the electron. So an electron's spin gives rise to a magnetic moment. So when L equals 0, when L equals 0, the magnetic moment of an electron is minus E over 2m into Gs into S. This is a vector, this is a vector. And this turns out to be minus E over m S. So there's a proportionality between the magnetic moment and the spin if the orbital angular momentum is 0. This constant, which relates the magnetic moment with the orbital angular momentum, is also called the Magnetogyric Ratio. Magneto for magnetism, gyric for orbital motion. The Magnetogyric Ratio. This is the proper SI name for this ratio. It's also called the gyromagnetic ratio. So whenever you have some kind of orbital or spin angular momentum, we can associate it with some magnetism, a magnetic moment. And that magnetic moment can respond to external magnetic fields. It can interact with other moments inside a solid or liquid and give rise to bulk magnetism and so on. So this is a starting point for study of magnetism. Orbital or spin angular momentum giving rise to magnetism, giving rise to magnetic moments. Now we would like to see how these spins interact and what are the proper Hamiltonians and how they respond to fields. This is the entire subject of this course. For example, for a proton also has spin. So for a proton we can have a magnetic moment as well. For a proton we have G. For a proton, the charge on a proton time over the mass of the proton into S. proton. Okay? So we have to use the proper value of G for a proton. Likewise for neutrons. For neutrons don't have spins. You just plug in the value of the charge on a proton, and replace this with the mass of the neutron. So these magnetic moments are experimentally determinable, and these actually determine what the spins are. So spins are measured indirectly. You do not have a spin meter, a meter that detects spin. You do it indirectly by measuring the magnetic degree of freedom. Magnetism is easy to detect. For example, a magnet will respond to external fields. So you perform experiments with magnets and magnetic moments, that's easier to detect. So this is the underlying principle of magnetism. And this object, by the way, is simply the Magnetogenetic Ratio. The constant of proportionality between the gyric degree of freedom and the magnetic degree of freedom is the gyromagnetic or the Magnetogyric Ratio. If this is the spin of a nucleus, you can have a spin of a nucleus, then this becomes the magnetic moment of a nucleus. It's called the nuclear magnetic moment. It depends on what the nucleus you're talking about. A nucleus will also have orbital angular momentum. Okay, so you have to take that into account as well. For an electron, remember, so if you look at this relationship, for an electron, for a simple electron, okay, let's look at this relationship for an electron. Let's take it further. This is a vector equation, we all know this. This is the mass of the electron. And we're talking only about the spin of the electron. Suppose you just take the z component of the magnetic moment. Now remember, this is an operator and this is an operator. So the quantum mechanical equation corresponding to this is simply U operator is given by minus E over ME S operator. Remember, we're focusing our attention on just an electron, the spin of an electron. Now if we measure the z component of the magnetic moment, you perform an experiment. Remember, whenever you want to perform an experiment, you have to break the symmetry. You perform an experiment by measuring the magnetic moment, but you measure along a certain axis because it's a vector. So you break the symmetry and you measure along the z-axis. You measure along any axis and you call it the z-axis. So if you measure along the z-axis, the magnetic moment that comes out is mu z equals minus E over ME times the z component of the spin. Now this z component of the spin is quantized according to quantum mechanics. So you have minus E over ME ms h bar. Ms is the spin quantum number that can take up two values, plus half and minus half. The spin is quantized, right? So ms could be plus half or minus half. So now you're performing a measurement. You have some magnetic moment associated with the spin of an electron which is pointing in some direction. You don't know which direction it's pointing in. You break the symmetry, you define an axis for the z-axis, and you look at the projection of the magnetic moment along this axis. This is how you perform quantum mechanical measurements. So when you perform this experiment, it turns out that mu z is quantized because this object is quantized. The possible values of mu z are plus minus E. Now this could be half, plus half or minus half, plus minus E over 2 ME h bar. So whenever you measure this magnetic moment of a single electron, isolated electron, not interacting with anything else, you measure its magnetic moment about an axis, you can only get two values. It's quantized. Okay? Now this is a constant. All of these are fundamental constants. Okay? So this constant is called the Bohr magneton. Bohr magneton. Okay? Just like the charge is quantized, and you measure charge in units of the charge on an electron, that's a unit of charge. Radiuses, lengths are measured in terms of Bohr radius, A0, 0.529 angstroms. Just in the same manner, the magnetic moment is measurable in these quantums, which is, each quantum is called a Bohr magneton. And this gives you the value of the Bohr magneton. So it's like a unit of magnetism, it's like a unit of magnetic moment. Its value is 9.24 into 10 to the power minus 27 ampere meter square. So this is the value of the magnetic moment you would get for an electron, only with its spin. I'm not talking about the orbital degree of freedom. Alright? Now we know that associated with the spin of an electron or a proton or any angular momentum there is a magnetic moment. Now we would like to do something useful with these magnetic moments. There are three kinds of quantities that we would like to talk about. We would like to talk about what is the energy of a magnetic moment when it's placed inside a magnetic field. That will give rise to different kinds of magnetic materials and different kinds of behaviors. We would like to talk about the energy. When placed inside a magnetic field which is denoted by B, measured in Teslas. We would also like to talk a little bit about what is the force that acts on a magnetic moment. Right? You place it inside the field, what force acts on it. Then we would also like to talk about what are the torques that act on magnetic moments. So these are the three kinds of objects, three kinds of quantities we would like to study, and these will open to us the door of magnetism. We're trying to put our step into the room. We talked about the spin of an electron or proton. Associated with this angular and spin angular momentum, there is a magnetic moment. Now we'd like to see how these magnets respond. Remember, each magnetic moment is just like a tiny magnet, just like a tiny compass needle, which can respond to external fields. So it will have a certain energy, a certain force, and certain torque. Now first, let's talk about the energy of a magnetic moment when placed inside a magnetic field. Now suppose any questions, you're most welcome to ask questions. A small class means more questions. Yes?
So for chargeless particle electron,
Which?
magnetogyric ratio.
Yeah, you then plug in the value of the charge on a proton there and the mass of the neutron. So remember, GQ over 2m is just a constant, which has been defined for an electron and a proton, but then you can divest it from the meaning of a proton and neutron. You can talk about general particles. Okay? You just have to then adjust the value of G. Okay? For a neutron, for example, Q is 0. So you put the mass of the charge on a proton instead, even for a neutron. Now energy. Suppose you have a magnetic field that's pointing in a certain direction and a uniform field. Now all of these concepts come from electromagnetism, and I hope you're all well comfortable with electromagnetism. So it's a uniform field. That field is denoted by B. Now we can represent magnetic moments by arrows. So it's a vector, so you can have a magnetic moment like this, magnetic moment like this, parallel like this. You can have a magnetic moment in an arbitrary direction. And at the back of your mind, conceptually or cartoonically or caricature-wise, this magnetic moment is associated with a positive charge circulating like this, right? A loop. But this is just a naive cartoonistic picture. You cannot draw a picture of a spin of an electron. But if you have current carrying loop, a physical current carrying loop, the magnetic moment will point like this. For this, there is a current carrying loop with a positive charge circulating in this direction, and so on. And then you don't need to draw these current carrying loops. So remember that each magnetic moment harbors some kind of angular momentum, which gives rise to this magnetic moment. So I will use the word throughout the course, magnetic moment, spins synonymously, right? A spin is a magnetic moment. So I will sometimes call these magnetic moments, sometimes I'll call them just moments, sometimes I'll call them spins. Spins is easier to say. Okay. So these are all spins placed inside the magnetic field. Now, each of these configurations has a different energy. The energy E of a moment placed inside a field is given by minus mu dot equal B. This is something you learn from basic electromagnetism. It's the negative of the dot product of the magnetic moment and the field. Therefore, this is the low energy configuration. The lowest energy configuration corresponds to this. When you have the moment that's anti-parallel to the field, that corresponds to the highest energy configuration. Right? Just whenever they are parallel, energy is negative here. When this is the case, energy is maximum. And when you have the magnetic moment perpendicular to the field, the energy will be in between. Okay? The energy is given by mu dot B. So the energy is simply minus mu B cosine of theta. So in order to minimize energy, you would like theta to be 0 degrees. So magnetic moments assume a low energy or a ground state if they are parallel to an external magnetic field. Now this concept, when you combine it with statistical mechanics, gives rise to a class of materials that are called paramagnets. Now suppose you have this box which contains a large number of spins. It could be electron, proton spins, and these magnetic moments are pointing in different directions. Okay, in different directions. And upon this box, you impose a uniform magnetic field B. Okay, in a certain direction, and it's uniform. Now different orientations of these magnetic moments will take up different energies. Now if you were to measure the magnetization of this sample, now I've used this word magnetization for the first time. Magnetization is a quantity which corresponds to the bulk properties of the system. It's a macroscopic quantity. It's measurable. It's a macroscopic quantity. And this means you just take the vector sum of all the magnetic moments inside the volume and divide this by the total volume of this system. You get the magnetization of the system. Now if you measure the magnetization of the system, this really means you are defining an axis. And that axis is the z-axis, the axis along which the field has been applied. So you get two possibilities. Either the spin could be parallel or anti-parallel to the measurement axis. This is quantum mechanics at work. But you have a large number of spins. So when you have a large number of particles in an ensemble, you resort to statistical mechanics. You resort to the statistical property of the system. And if I would like to find out the number of, okay, let's suppose that if this is the magnetic field, and the spin is parallel to the field, you call this the state alpha. Okay? And since it's a quantum state, put a ket with it. And if the spin is anti-parallel to the field, you call this state beta. Okay? You could also denote this by this carbon, or you could denote this by this carbon. So these are the two possibilities of spins that you will measure inside the system. So now there are n spins. The total number of spins in this system is capital N. If I would like to find out the fraction of spins that are in the state alpha, how am I able to find out this fraction? What is this fraction going to be equal to? The temperature of this system is capital T. What's the fraction of spins that will turn out to be in the state alpha? Use your basic knowledge of statistical mechanics. Anyone? Yes, yes, it's the Boltzmann relationship. The Boltzmann relationship tells that the fraction of spins in the state alpha is given by the exponent of the negative of the energy of the alpha state divided by kBt, the Boltzmann constant. And for normalization, you have to divide all of this by what? The partition function z. Likewise, if I would like to find out the fraction, remember this is a fraction. This is a fraction. The fraction of spins in the state beta is given by minus E alpha b. And you know what these energies are. These energies are simply this, plus minus mu b. First of all, let's find the partition function for this system. The partition function for this system, z, is given by exponent minus E alpha kBt plus exponent minus E beta kBt, right? This will normalize the fractions, right? This is the partition function for the spin half system placed inside a magnetic field. Now we know the values of E alpha and E beta. So if I go here, z equals exponent. Now E alpha, let's find out E alpha and E beta. E alpha is the low energy state is minus mu b. What's mu for an electron? It's simply the Bohr magneton, mu b. E beta is plus mu b. So these are the energies of the alpha and the beta states. The magnetic moment of a single electron with just a spin is the Bohr magneton. We've already derived that. So we know what the energies are. So we can simply plug in these values. This becomes mu b b over kBt plus exponent minus mu b b over kBt. This is the partition function, and this is nothing but 2 times cosh of mu b b over kBt. Okay, so we've derived the partition function. This is the partition function for a spin half inside a magnetic field. The field has magnitude B, the system is at temperature T.